this computer. I'll delete that one. Okay, good. I think we're recording. Okay, share screen. Okay, so hopefully everybody sees, and it's similar on it's similar on the in-person website as well. It's looks about the same. You'll get these same options. Okay, what I'm going to do now, let me turn on the, well, so maybe what I'll do is work through one of these.
So the review, not the review, but the links for like the videos, which one is it?
The links for the videos?
Yeah.
Okay, well, so I'll show you those too. Who's asking that? Shane?
Yeah.
Okay, so well, so let me do this real quick. Okay, so we'll do that in here in a second. Okay, so let me go back here. Let me go to the A website. So then, see, I think they have those. Yeah. F21. Okay, yeah. Okay, so that was it. Yeah, that was something else. Okay. Let's see. Yeah. So if you look here, you see it says videos S20. So here they are. And no, those are not the right ones. Should be S21. Scratch that. Videos S21. Okay, well, hell. Video lectures. Here, let's see. Nope. I don't know. We haven't used them much on this website, so I'm not really sure. Okay, I'm sure. Oh, I swear to God. Let's see.
I saw something S21, but I think that's project or something.
Yeah, it was.
We could continue with the material and then you could do that afterwards.
No, I'll do that. Okay, I think, oh, maybe I did put them, let's see. Oh yeah, they're here. They're here in the F21 folder. Okay, and then if you go down here all the way towards the bottom, Zoom final review right here, and then review for S21 final exam. So you could do both of those. Those would be good. I probably should just play that. But so that's where they are. And that's true for the B class, the online class too. Okay. Now, let me switch this over here, and actually I'll probably switch. Let me stop share, and then I will share screen again. Only I'll do this one. Let's see. I guess it's really this one I want to share. And, okay, can you see that fairly well?
Yes, sir.
Yes. Too much. Yes. Okay, so let's go through this. So I'm going to work through this, and then I'll give you a chance to ask questions, or maybe I'll take a little bit of time and try and cover some things specific to the actual test. Let's see. Let's do this real quick. See where we are. This is 2015 main. So this would be. So I want, let's see, I guess I need to do it this way. Online questions, S20, yeah, okay. S21. Okay, let's do type. And okay, here. And all right, I'll put this over here and we'll go through this in a little bit later. Okay. All right. So let's go through this first. Now let me bring up the projector. So it's H, A, B, C, D, H, I, J. This is it. Okay. And let's see, turn this on. Start camera. Okay. Good. All right. And then, so yeah, perfect, I think. Yeah. Okay. That's good. No, we want this to rotate. We want it to rotate all the way like this. Okay. Yeah. Okay. Okay. All right. So we'll work this. Okay. So so here's this test. So and then we'll work this here. All right. So the first problem. So there will be a couple of SOP to PO. There'll be one SOP to POS and one POS to SOP. So you should review that. It won't kill you if you miss it. But all right, so let's look at this one. So this is A plus B plus C prime quantity times A plus C plus D prime quantity times C prime plus B. All right. And so the first thing you want to do, you want to see if you can use any of the simplification theorems. Well, so do we have a B with a C prime? There's a B with a C prime. So we can get rid of this entire term. And that leaves us with this. And now we have A, C, and D prime, and we have a C prime and a B. So
we can't see your paper.
You can't see it?
No, sir.
We can see the test and we can see your video.
That's because I selected okay. Yeah, let me fix that. That's easy to fix. I just forgot what I did. Okay. Now you can see both.
Thank you, sir.
Yeah, okay. Yeah, no problem. I meant for you to see it. All right. So
rewind, start over.
Yeah, okay. Well, so if you look at, here's the equation. So you have A plus B plus C prime, right? A plus B plus C prime. And then you have A plus C plus D prime. And then you have C prime plus B. But you could, of course, rewrite that B plus C prime. And now look and see if you got a B plus C prime. Oh, yeah, right there. So because this term is a subterm of this term, you can just delete it. That term's included here because you know that you could have A plus B plus C prime and A prime plus B plus C prime, and they could combine to this. So obviously this includes both of those terms. All right, so now we just have A plus C plus D prime and B plus C prime. Well, we have a C and a C prime. So, and that's really the only common terms. So we can use the M and F. So we'll rearrange this then. C plus A plus D prime times B plus C prime. So we can take this times all that, and this will go with that. So that gives us BC plus C prime times A plus D prime. And then you just distribute the C in there, and you get BC plus AC prime plus C prime D prime. Okay. So that's that one. So of course the key to making it easier is to realize that you could delete that one term. All right. So let's scroll this up. And now we'll do this one. All right. So now we have it in, what form is this in? SOP or POS?
SOP.
Yeah, it's in SOP form. So let's go to POS. Okay, so we have to change it. So the first thing we're going to do, so we have ABC plus B prime CD plus A B prime C plus A B prime C D prime. Okay, so we're looking for an A, B, C. Okay, so there it is. So that's good. So we can get rid of that. And then can we delete anything else? Or can we combine terms? Well, here we have a B, C and an A, B prime C. So we can combine those to A, C. And then we're just left with this term plus B prime C, D. B prime C, D. All right, so we've got a C in both these terms, so that's nice. So now we can use the second distributive law instead of the M and F this time, and we'll take C out, and we get A plus B prime D. All right, and then we can apply. Actually, we use the first distributive law. Sorry, and now we use the second distributive law on A plus B prime. So that's going to give us C times. So we'll let this be X, and this is YZ. So it's going to be A plus B prime quantity times A plus D. So we have this degenerative term there that's just all by itself. And then we have two POS terms. Okay.
I had a quick question.
Sure.
Whenever you canceled out the second and the fourth term, we have B prime CD, and then on the fourth one we have A B prime C D prime. The D's aren't the same, so you canceled out the A, but we also have a difference of D's on your second line. C plus B prime CD. Where you got the B prime, or how did you get the B prime CD? That's what I'm asking on the second line.
Okay, let's just go through it again. So we started with ABC plus B prime CD plus A B prime C prime, A B prime C plus A B prime C D prime. Okay, so the first thing we saw, we had a B prime C. Maybe did I copy that wrong? Oh, maybe there was a D prime there. Oh yeah. Yes, that's a good point. Okay, so I misinterpreted that. I thought I had a D prime here, but I didn't. Okay, so that's a problem. But I do have, oh no, I had an A B prime C. I used A B prime C with A B prime C, and the D prime doesn't matter because that's the same as X plus XY equals X. Okay, so in this case, X equals A B prime C, and the XY equals A B prime C D prime, or the D prime is the Y. So we get rid of that term and we're just left with the X. Okay. And then, so then I take all these terms, then I took this term and combined it with that term to give me AC. And so these terms are gone, that term's gone, and I'm just left with this plus AC. So that's AC plus B prime CD. All right.
So how did you get the B prime CD out of that on the second row?
This just came from here. I didn't do anything to get that.
Oh, okay, I got you. Sorry.
I just brought that down. All right. Are we good?
We're good.
All right. Okay. So let's do the next one. So now let's look at this one. So now we have and I think there'll probably be a similar problem on the test. Again, this is just kind of review, right? Here's a truth table. Here's a K-map. So we're going to go through and we're going to put the ones in.
Dr. Morton,
Yeah.
just before we move on, there's a question in the chat about that previous one from Jacob. Can't we just put them in a K-map and solve it?
Yeah, you can. Yeah, you're welcome to use K-maps to solve these. Yes, you can do that. Yeah. So if you want to do that, yeah, have at it. Perfectly okay. Yeah.
Thank you.
I used to require you to show work, and then you could use the K-map to check it, but this is an online test, and so just do whatever, do whatever you can do to answer the questions as long as it's your work. All right. So let's do this one. So let's see, we'll bring this up and maybe move it over. Okay, so first thing we're going to do, we're going to take this truth table and put it in a K-map. Okay, so here's our K-map. Okay, and we're going to do AB up here and CD down the side. All right, so all right, so we just follow this. Remember, this is the 0 row. That's the 1 row, 2, 3. That's the F or 15 row. So this is 0, 1, 2, 3, and so forth, where you have to switch the bottom 2 rows, switch the rightmost 2 columns. All right, so 1, and I'll just put in the ones and the don't cares. 2, the X goes here because we have to flip the rows. A 0 would go here, but I'm going to leave it blank so it's not so cluttered. And then we'll do 1, 1, and 0, 0. And then we'll do 0, 0, 1, 1. So that's 0, 0, 1, 1. And then this column will be don't care, 0, 1, don't care. So don't care, 0, 1, don't care. All right. So what you can see, we want to do all the prime implicants. So we're going to circle that. We're going to circle this. I think it ran out. Switch that out. Hang on. So we'll circle this. And now we also have to include the prime implicants with the other don't cares, but obviously this would be our solution, right? We don't need these other don't cares in the solution, but for purposes of prime implicants, we do. So let me see what the actual question said, because I don't remember. Whoa. Okay, so plot a K-map, write out the min POS expression and indicate the required values for don't cares. Okay, so I'll write out the SOP and the POS both. And then on the circle all the prime implicants. Okay, so the other prime implicants, which I could circle here, would be this one here, this one here with this one, and this one with this one. So these 2 little X's themselves bring in 4 more prime implicants. Now they're prime, but they're hardly essential. In fact, the don't cares make them completely they're non-essential. You don't even need them in the solution. Okay, so the SOP solution would be these 2 terms. So this term would be A prime, C prime, and this term would be AC. Now, this is easy to switch to POS form. Since I have A prime, C prime plus AC, I can use either one of these variables and do M and F. So, which is our second simplification theorem. So we'll just do this. And that's going to give me A plus C prime quantity times A prime plus C. So that's the POS solution. This is the SOP solution. Now I could also put the zeros in here and here and here, and I could draw a circle there and a circle there. That would be their solution. And I would write this would be A prime plus C, and this one would be A plus C prime. And I get the same thing. Okay? Everybody good with that?
Yes, sir.
All right.
Professor,
Yeah.
Do we need all the other extra prime implicants on the test, or will you?
No, if I say circle all the prime implicants, yeah, so how many prime, yeah, not the zeros, just the ones. So if we draw this again, okay, we'll just draw it smaller here and quicker, but so we have 1, 1, X, 1, 1, X, X, 1, 1, 1. Okay, so the two obvious ones are this one and that one.
Right.
But absolutely legal and totally legitimate prime implicants, this one with that one, this one with that one, and this one with that one. So you have 1, 2 groups of 4 and 1, 2, 3, 4 groups of 2. So you have a grand total of 6 PIs in this particular problem. And no, you can't ignore the fact that you have the don't cares. You have to consider them as prime implicants.
All right. What does it mean? But why does it have the equal signs next to the X on the?
So in this particular case, I don't guess I used that. But what I might have done is ask you to list how we take them. And in this case, we would take this X, we would take as a 0 for the SOP solution. We take that X as a 0. We take this X as a 1. This X as a 0 and this X as a 1. For the POS, we do the exact same thing, 0 and 0 and 1. So we wouldn't use this don't care because it's right there. It's this one right there for the POS solution, because we'd use this X for this group of 4 up here. We'd use this X for this group of 4 zeros down there. But for the SOP solution, we would use this X for this group of 1s and then this group of 1s up here. But we would take this X and this X as 0, so we wouldn't have to include any of those other non-essential prime implicants in our solution. Okay.
Okay.
So you get to choose. What?
Sorry, go ahead. Would an X by itself be considered a prime implicant?
Yeah.
Like on an island? Okay.
Yeah. I mean, yeah. It would. Yeah. What you do in that case? Go ahead.
I think we're getting feedback on the computer.
Yeah, I can't hear very well. So yeah, if you're not asking a question, you probably should mute your audio. All right. I don't know, maybe I can mute. No, that doesn't work. Anyway, that one muted. All right. Oh, maybe it is. Okay, I think everything's good now. Okay, fine. All right. Okay, we good? Let's keep pressing on. So, so the next one then. So this is VHDL code. Now the in-person we did Verilog code because that's what I'm switching to. But we did VHDL code here. All right. So, all right. So here's the code in VHDL. Now in VHDL, we have to have an entity which is separate, and then we have an architecture which is separate. And the architecture borrows the port list from the entity. The entity is always the port list. And so here's the entity. It's called flip-flop. And here's the port list. D, clock, clear, set not, logic, inputs, standard logic, and Q and Q prime output standard logic. And then here's our description of, for this particular architecture, we're going to use, it's going to be flip-flop A of flip-flop. So it's going to use this entity. And its signal then is standard logic. It's going to add one signal called temp. All right, so now we bring, and that's going to be an internal signal, not in the port list, which is up here. All right. The port list is what talks to the outside world. And then we have, instead of an always block in Verilog, we have a process block in VHDL. But these signals here are in the sensitivity list. But in this case, we don't give them edge designations directly. The edge designation for the clock comes from this line here. And it's this idiom called clock tick event, and clock equals 0. When you see clock tick event, that tells you that it's an edge. And when you see clock equals 0, it means that it just fell. The edge just occurred, and now the clock is 0, which obviously for it now to be 0 right after the edge, it has to be a falling edge. If clock is equal to 1 after the clock tick event, then it's a rising edge, and that's how VHDL does it. Okay, and then you have an if statement here. If clear is 1, so then temp equals 0. Else if set is 0, then temp equals 1. So you have a clear and a set. And then if both of these are not true, then you check this, and that's did the clock just tick and now it's 0? Well, in that case, then temp equals D, which is what the D flip-flop does, right? It's going to set the temp to D. And then outside of this, we have continuous assignments, same, just like in Verilog, where these anytime the right side changes, the left side is updated. So temp changes in this process block, and so we update Q. And we update Q as temp, and then Q prime is updated as not temp. And in this one, in VHDL, we don't use the ampersand or the tilde. We use the word not. So it's just a little different. Okay, so now some questions. So what kind of flip-flop does it show? Well, it shows a D flip-flop with an active low set and an active high clear. How many bits can it remember? Well, all flip-flops remember 1 bit. What do we call clock, clear, and set not in the first line? Well, down here, it's not really the first line. It's the first line of the architecture. And we call that the sensitivity list, just like we do in Verilog. Is the clock rising or falling? So in this case, because of that, it's falling, right? And then label the 3 blanks. Okay, so what would you label this input here? What would that be labeled? A, B, and C. So what's C?
Clear.
What?
Clear.
D.
Yeah, that would be the D input generally. And then what about up here? A, it could be the clear, and then the B could be the set not. And then add bubbles. Where do you need bubbles?
Top. Oh no,
Set
the
not.
bottom.
On the clock, where the
On the
clock
clock.
is.
You need
Yeah.
1 on the clock, and you need 1 on the set not, which would be the A, I guess, if you put it there. Okay. And then if clear equals 0 and set not equals 0, what does Q equal?
1.
Yeah, that's right. That's because the clear is active high, so it wouldn't do anything. But the set is active low, so it would force it to a 1 state. And then D would be ignored, but you're not even told what D is, so it doesn't matter. All right. So I don't think I have a question on this, but if you do, you can use your calculator. It shouldn't be that big. Just remember, if I can't remember if I have a question, but if we do do a 2's complement, remember you want to pad it out to whatever number of bits you're required to use. And remember how you know how many bits various things can hold. So just to kind of quickly review that, if you have something that's let's say we want to put 100 and we want to make that a 2's complement. Okay, so how do we make a 2's complement? How do we make 100 a 2's complement? Well, first we switch it to decimal. I'm not going to do that, but let's say it's, well, I don't know. Hell, let's do it. Where's my thing? did he just, oh, I think my little preemie just passed his car seat test. Oh, he's just taking it. Yeah. My daughter, my youngest daughter just had a premature baby 3 weeks ago. And he's ready to go home, but he has to pass this thing called the car seat test. It's really crazy. He has to sit in the car seat and not drop his O2 sats for 2 hours. All right.
Well, congratulations.
Yeah, he's done really well. It's very exciting. He could have had a lot of trouble, but thank goodness he didn't. But you never know. But it's been a little, they thought he was coming home Monday and then he flunked his car seat test. He made it for an hour, but then he desatted. So anyway. So they gave him some Epogen to get his red cells up. And so now hopefully he's doing better. All right. Decimal and binary. Okay, so 100. Convert. Okay, so it's 1100100. So this is 1100100. Okay, so that's our binary. Now, notice how many bits. So it's 1, 2, 3, 4, 5, 6, 7. It's 7 bits. Okay, what is the biggest? What's the biggest? So if we have unsigned, unsigned 7 bits. What's the biggest number we can hold in an unsigned 7-bit variable? So 2 to the 7th minus 1 because
127.
128.
Yeah, it's 128 minus 1 or 127. To represent 128, you need 8 bits actually, because you have 0 to 127. So you can represent 127 different things, but you have to count 0. So the biggest number is 127, and that would be 1111111. That's 127. Okay, so can we fit, if this is our number 100, and the biggest number we can fit is 127, can we fit 100 as a 2's complement, so a minus 100 into 7 bits? In other words, in 7 bits, can we go from minus 100, or maybe more than that, all the way to plus 100? Well, how many things would that be? That would actually be, yeah,
200.
201 things is actually what it would be, counting 0. So, and we can only fit 127s, so it won't fit in 7 bits. So you should always remember, we'd have to pad it out to 8 bits. You got to put a 0 there. And now you can switch it to 2's complement and it'll be okay. But if you don't put that 0 there, when you switch it, it's going to be all screwed up because it's starting out with a higher order bit as a 1, which obviously means it's
negative.
It's negative now. And when you complement it, it's going to be positive. It's not going to be right. So you have to pad it out. So just always remember, in any given number of bits, you can only represent, like in 8 bits, okay, you can represent minus 128 all the way to plus 127. And you get exactly the same number of negative numbers as positive. It's just that 0 counts. So you also have to count 0 in this. So you get 127 plus the 0, which is 128 positive numbers and 128 negative numbers, minus 1 to minus 128. All right. So, but I don't think that's on the test. So that was just a little bonus. All right. So here we're looking at, so given this K-map, loop the term for the minimum solution. Well, obviously you'd group these and you group these. So you'd have 2 4-bit groups, right?
You could group the one down the center too.
Yes, you could group this one too. That's a consensus term. It's a totally legal term. It is one of the prime implicants. It's a non-essential prime implicant because it's a consensus term. And you would add this in if you had a hazard, and that could fix the hazard. So that's where it comes into play. So loop with dashed lines any consensus terms, the one down the center. Circle which transition would cause a hazard. Well, transitioning from this term to this term, or from this term to this term, could cause a hazard. And that's where adding this consensus term would prevent that from being a problem. And then you would likely need to add this consensus terms in situation when the downstream logic was very slow, true or false.
False.
That's correct. It is false. So that's because the downstream logic matters. And in this case, if your downstream logic is really slow, a little, few nanosecond glitch isn't going to cause any problems because nanoseconds are really fast. And downstream logic that's slow is not going to be operating anywhere near nanosecond frequencies. So it may not even be in tens of megahertz. It may be down in kilohertz frequencies. That would be slow, maybe even lower than that. So it won't cause a problem. Shouldn't be a problem at all in that case. And then write the consensus term. So what is the consensus term in this case?
The meta rule I just mentioned.
Yeah, it's
CD.
easy. CD, right? Yep. So it's CD. Okay, moving on. So let's look at this one. So here's a sequential circuit with an input X and an output Z. The logic, the output is opposite of what the input was 2 clock cycles earlier. Okay, and then there's some little example data. And so we want to look at the example data. So the way to think about this, it's a little screwy, but the way to think about it is, so you have to remember the 2 previous values. So every state basically, so we have 4 states here. And the first one, the 2 previous values were both zeros. And in this one, the 2 previous values were 1. So that's easy. So we know that the output then should be, when we leave this node, doesn't matter what X is, but the output should be this 0. And we write it, this would be the oldest 0, this would be the newer 0. And then maybe we get another 0. And when we get that next 0, we output that last 0. Here, it's a little confusing. And so here your last output was a 0. So that was 2 clock cycles ago. So when you get the next value, that's what you output. Here, your last value is a 1. So let's see if we can figure this out. Okay, we start in S0. And in S0, we'll assume all our previous values. Let me do it down here. Let's see, I'll move this up a little bit. And also we'll talk about whether it's a milli or more. But let me put this up here. Okay. All right, so we start in S0. And what we're remembering is we're assuming all our previous inputs were zeros. And now we're going to get our first new inputs here. Okay. And so if we get a 0, obviously we should stay here. And our oldest value is this 0. So we get a 0, we output a 0. Okay, now if we get a 1, we can go to S1. On a 1, we still output the 0 because that was the value 2 clock cycles previously. All right. Now in S1, we got our oldest one was this 0. Now it's slid back here. And our newest one is this 1. All right, we're in S1. So what we're remembering is our oldest value is a 0, our newest value is a 1, and then we're going to get another value. Okay, so if we get a 1, now was there a question? No, okay.
Sorry, Professor, that was me.
Okay, control yourself, Jose. No, that's fine. All right. Okay, so if we get a 1, then we're going to have to go to S3. And because our last 2, this one slides over and then the next one pops in. So this will be the oldest one now. So that's what we're remembering in S3. Now, if we get a 0, then that one will slide over and we'll go to S2, where we remember 1, 0. Okay, so this is on a 0 and we output a 0 because that's our oldest one. And here we get a 1, but we still output a 0 because that's our oldest one. Now from S3, if we get a 1, we can just stay here and we'll output a 1 because that's our oldest one. if we get a 0, so that now the 1 slides over, now we have our oldest one, or this one slides over. So now we have a 1 here, and our new one would be a 0. So now we got 0, 1. So in this case, we would go to here. And so that would be on a 0, and we would output a 1. And then from S2, if we get a 0, now we're going to have 2 zeros. So we have to go here and output a 1. And if we get a 1, then we're going to have 0, 1. So now we're going to go here on a 1 and output a 1. So it's a good little exercise to see if you can just think your way through this. It is confusing.
Yes, I'm confused.
Okay. Well, this is where you have to train your mind to be a steel trap. Okay. You just have to think about this in a very disciplined way to beat the confusion. And so let's go through it again. Okay. You're in S0. So what are we remembering? In S0, we remember that our last 2 inputs were 0, 0, right?
Yeah. Uh-huh.
In S1, we remember our last 2 inputs were 0 and 1. The oldest was a 0, the newest is a 1. And then we're going to get another one and go someplace else. In S2, our oldest is a 1 and our newest is a 0. And in S3, our oldest and our newest are both 1s. So because of the symmetry involved here, once you figure out the paths associated with 0 and 1, then you know the paths for 3 and 2 should be the mirror image of those. But anyway, so whenever you want to figure out, in this case, what's your oldest value? Well, it's what are you going to output? You're going to output. So what does the actual thing say? It says the output is the opposite. Oh, okay. I lied. The output is the opposite of what the input was 2 clock cycles earlier. Okay, well, I made it the same in this case, but you could do it with the opposite too. But anyway, okay, so forget that. I think I changed the problem from a previous year or something. I can't remember if I've asked this one or not, or something similar to it. But
So that means that this one that we worked out here is wrong pretty much because it's not doing what the question asked. We did it the same instead of opposite, right?
now it's correct.
Funny.
Yeah.
So this is a Mealy circuit?
Yeah. Remember, all you have to do is look at this, and the output depends on X. So you know it has to be Mealy. Right?
Yes.
Okay. Does everybody see how you look at this? As soon as you see X equals 0 and X equals 1 in the output column, you know that it doesn't depend on the state. It depends on the next input. If it depended on the state, then there would be no X's in this output column. You just have one number, one output associated with each state.
Oh, makes sense.
Now, of course, we know from doing our state machine charts that our outputs we can have Mealy outputs and more outputs in the same problem. Some can depend on just the states, and then some can depend on the state and the next input, which would be Mealy's. Okay. All right, let's go on. Good question.
Yeah, I got a little confused on the after you went to S3. I understood how you went from S0 to S1 to S2 to S3. And
Well, from okay. So from S2, we can't get to S3 because you see you've got a 0 as your newest input. So no matter what you get for your next input, you're either going to have 2 zeros, or you're going to have the oldest be a 0 and the newest be a 1. So you're either going to go to S1 or S0. And from S1, you can't get to S0 because you got a 1 here. Mm-hmm. So your newest input is going to be 1s. If you get a 0, it's going to be 1 0. So that would be S2. Or if you get a 1, it's going to be 1 1. That would be S3. From S3, the only place you can get to is S2. From S0, the only place you can get to is S1. You can stay here on a 0. You can stay here on a 1.
Okay.
Does that make sense?
It does. It does.
Yeah, but you just have to think through it. And the way you think through it, and let's just do it again, because it's really easy. See, it's part of the key is just getting a little mental discipline in how you approach these and not just freaking out, right? So you're going, yeah, I got this, no problem. All right, so let's just do it again. So we start in S0, and we know that all our previous inputs were 0, so that's where we remember 0, 0. All right, if we get a 0, we still have 2 zeros, and we output either the same or the opposite. If it's opposite, we'd output a 1. We'll do it for the opposite. Okay, so now we're doing opposite. All right, now if we get a 1, now we're going over here to S1, where we're going to remember our oldest input's this 0, so it's become this, and our newest input's the 1 here that brought us over here, and it's right there. And then what are we outputting? We're outputting the opposite. So there's a 0. The opposite of what it was 2 clock cycles previously. It was a 0, so the opposite's a 1. Okay. Now we're in S1. 2 possibilities. We get another 1. That sends us all the way over here to S3, where we remember 2 1s. And we output the opposite of 2 clock cycles earlier. It was a 0 2 clock cycles earlier, so now it's a opposite 1. And then if we get a 0, then we go, now we have oldest is 1, newest is 0, so now we need S2, where we have 1 0. And we go there on a 0, and we output a 1 because our oldest is a 0. And then in S3, stay here in a 1 and output a 0 because it's opposite. Or if we get a 0, go here and output a 0 because it's opposite. And then from 2, if we get a 0, we're going to go to here and output a 0 because it's opposite. And if we get a 1, we're going to go here and output a 0 because it's opposite. Okay? Does that make you happy, Shane?
Yeah, thanks.
Good.
Thank you.
All right. Yeah, so that's, and how about that, Jose? Does that make sense now?
Yes, sir.
So that's how you think about it. You just think your way through it. Okay, we're going to do some more of these. That's the whole point of doing this review is to do some of these. All right. Okay. All right, let's see. We'll find some more. Okay, so, here's a good one. So there likely to be a problem like this on the test. Okay, so this is going to be, we're going to count 7, 3, 1, 0, 5. Now, in this case, there's no repeated sequences, so we can use our standard method. We don't need the extra columns for the outputs. We'll just let the next states represent the outputs. So effectively, this problem, the only real input here is a clock, and there's no real input, just a clock, and there's no outputs, just the state of our next state flip-flops. So we have 3 flip-flops, A, B, C. Here are the desired next states, and these are real easy to do. So obviously, what we want to do here, so we have A, B, C, and our next state, A, B, C. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 1, 2, 1, 2, and 1, 2, 3, 4. Okay, like that. Okay, so what's our desired next state from 0?
One zero one.
That's right. Yeah, we go to 5. And what's our next state from 1?
0,
0, 0, 0.
Yeah. And what's our next state from 2?
Don't cares.
Don't cares. What's our next state from 3?
Don't. Zeros.
0, 0, 1.
Yes.
And how about 4?
Oh,
Don't care.
Don't cares. And how about 5?
1, 1, 1.
Yes. And how about 6?
don't cares.
Don't cares again.
and 7.
011.
Okay. All right. So that's it. Now all we need is 3 K maps. And we take this column and put it into the A, this column for the B, this column for the C. And we just have to remember to flip the 2 bottom rows because they're going to be 3 variable maps. So we'll do them over here. 1, 2, 3, and here we'll put A on top, B, C down the side. And so this will be 1, 0, don't care, 0, don't care, 1, don't care, 0. So looks like, so this is not too bad. We can do that. And then that has to be that. So this would be what, C prime plus this little group, A, B prime. Everybody agree with that?
See,
All right. C as in yes.
yeah.
Good. All right. And then we'll do the DB. Same idea. All right. So we just do 0, 0, don't care, 0. And remember, the don't cares should always be in the same places unless you got some kind of 5 variable thing or something weird. All right. So, all right. So 0, 0, don't care, 0, don't care, 1, don't care, 1. So this is easy. So that's just A. Okay. Don't need this because it's a don't care. So you take that one as 0. All right. And then finally the B or the D, the C rather. All right. So 1, 0, X1, 1, 0, X1. Don't care is 1, don't care 1. Remember, the don't care should always be in the same places, at least when they're in the same rows. All right, so this looks pretty good. We get this, we get this, and we get this. This is crazy, but it's going to be, so this is so that's A, B, C. So this is B plus A plus C prime. So A plus C prime. Is that right?
Would you have to do any reduction here, or you just
No,
want to
sorry, a B, not C. It's B. A
Would we have
plus
to
B
do-
plus C prime. What's that?
Would you have to do any reduction here, or you just want us to do that?
You're using the K maps. So yeah,
Okay.
the K map should give you a reduction. Should
Okay,
give
but I
you-
remember when we was doing it in class, it said that when you write down all of the paths to A, whatever,
So when
that's 1 and all that stuff.
yeah, that
um,
was when we were using that's when we were using SM charts, and we didn't necessarily take into consideration the don't cares. But these K maps have don't cares in them.
Okay, so that is not needed for this.
Right. You're already getting the minimum solution because you're using K maps and you put in the don't cares.
Okay.
All right. All right. So does this circuit have a clock? Yes, it does. Okay, here's a state machine. So let's look at this. All right. So you're to finish a state machine chart for the problem. Maybe what I'll do, let me print this page out. Let's see, what is that? Page 2. Page 2. Yeah, page 2. I'll just, yeah, put print. Just print.
If you print on both sides, you save more paper.
Yeah, my printer will do that. I just never do it. So hang on, let's see. That's not the right one. Okay, screw it. We'll just print the whole thing. What did it do? What? This is driving me crazy. Print. Okay. Oh, I see it. Printed. Okay. Okay, let's print this and then I should just printed all the pages out. Yeah, I want to print page 4. All right. Okay. Okay. So let's first do this one. Okay, so here's another problem. Okay, can you guys hear me still? Yes.
Yes, sir.
Yes.
Okay, everybody can see this, okay?
Yes.
All right, good. All right. Okay, so let's read the problem. Design a Mealy sequential circuit having one input and one output that will produce an output of 1 whenever 4 zeros are input in a row and 0 otherwise. Resets as soon as a 1 is received, but overlapping targets are allowed. All right, so, okay, so here's our test sequence. So let's see, let me straighten this out and then do that. Yeah, that's better. Okay. So X comes in, we get a 1, then we get 1, 2, 3, 4. So that 0 is replaced with a 1. And then we have another one and another one, all replaced with 1s. And then we get a 1, so we're reset, have zeros, and then we get a 0 and a 1 and 2 zeros and 1, 1. And then we get 1, 2, 3, 4. So now we get another 1. All right. So we're going to output 0. So Z is going to be 0, except when we have 4 runs in a row and overlapping targets are allowed. Okay. So we'll start in S0 and we're going to use a Mealy. So we're going to start in S0 and we're going to and in S0 then we have nothing. Okay. So we get a 0 and we go to S1. We get a we get a 0 and we go to S1. Okay. And if we get a 1, then we can just stay here and we still have nothing and we output a Z of 0, right? All right, now we're in S1. If we get another 0, we can go to S2 and we still output a 0 because we don't have our target. And in and if we get a 1, then we're back here with nothing again and output a 0. In S2, if we get a 0, we're going to S3 and output a 0. But now we have 1, 2, 3 zeros in a row. So we're working on the 4. And then, but if we get a 0, then we're going to have to go back. Sorry, if we get a 1, we'll go back here and output a 0 because now we don't have any zeros in a row. In S3, we have, so here we have 1 0, here we have 2, and here we have 3. So if we get a 0, that's 4 zeros. So on a 0, what should we do? Well, we should stay here, but output a 1. If we get a 1, we're back to S0 and outputting 0. We don't have anything again. Okay. So you see how I just kind of think the way through it?
Now, why would you stay at S3 if you get a 0? I thought you were supposed to reset when you get the target.
Okay, so read the problem again.
The reset section as one is received.
But overlapping
See.
targets are allowed. And then remember our little example sequence. So we got 0, 0, 0, and our fourth 0, we outputted a 1. And then we got another 0, so that was another target, and another 0, that was another overlapping target.
Okay, so that means that we just looping.
So that's it. Yeah, right. So that's why we're staying here, so that we can, if we get, each time we get a 0, we're just staying there because we still have 3 zeros in a row.
Oh, okay. So even if we get 4 zeros, we just gonna go back to there. 5, go back to there.
Yeah, there's no real logical difference between having 4, 5, 6, 7, 8, 10 zeros. What we're really interested in, if the next X in is a 0, that meets the 4 zeros in a row criteria.
Okay, makes sense.
And that's only because we're allowing for overlapping targets. If we didn't allow for overlapping targets, then we would reset. We wouldn't stay there. And you'd have to get 4 more zeros in a row to get the next Z equals 1.
So for every time we get that fourth 0 is going to be output in 1 all the time.
Yeah, in this case, you're allowed to have overlapping targets. So really, the way this works is you have 3 zeros in a row. So then on the fourth 0, Z equals 1. So this is your group, this is your group, this is your target. But then if you get another 0, this is your new target. And it's overlapping the other one.
Okay. And another 0, you do the same thing and so on.
And that's why you get another 1 at Z.
Right. Each time you get another 1. You get a 1 here, you get a 1 there. And if you had another 0, you'd have another overlapping target. And you get another 1 there.
And how is that?
That's only because that's how the problem stated.
Right.
There's nothing magical or necessarily required about that.
How is that represented on the graph?
On the graph?
Yeah, like
with
the
this
overlapping.
With this little arrow here that says we stay here when we get a 0 instead of resetting.
Got it. Okay. And so when we get a 1 from S3, that's
this one?
Yeah.
That means we got a 1. So now we have no zeros. So we go back to S0. We have nothing.
Okay. Got it.
All right. Yeah, I don't think I'll do that one. And
hey, Professor, I have a little bit of a family emergency that just happened. Will you be posting the video?
Yeah, I'll put the video online.
All right.
Yeah, I'll put it in the video folder.
With the video 2021.
Yeah, I'll put it in the fall 21 video folder. Yeah, sorry. I hope your emergency is okay.
Yeah, accident. I gotta go pick up my girlfriend.
Oh, no problem. That's not good. All right.
Thank you,
Okay.
sir.
All right. No problem, Jose. Okay, let's do this one. Actually, I got it online here too, so we'll do. Okay, so let's look at this problem. So we'll do this problem, and then I think I'll ask a few just general questions, and then let's give you a time to ask questions. Okay. So here's a good example. Okay, so let's read it. So you're to finish a state machine for a problem with an input X and an output Z, where Z equals X, except it must prevent 4 zeros in a row. Oh, well, it's the same problem. If the input is 0, 1, 0, 0, 0, 0, 1, 0, 1, then the output Z should be 0, 1, 0, 0, 0, 1. Where the one that is underlined would have been a 0, but it was changed to prevent 4 zeros. Okay, so it's a little bit different. In this case, Z is the same as X, except if there's 4 zeros in a row. Whereas on the other problem, Z was always equal to 0, unless we had a target of 4 zeros. Okay, well, anyway. Net resets after the target. So in this one, we're going to reset. We're not going to allow for overlapping targets. Yeah. Use a Mealy machine. Do straight binary flip-flop state assignment for each block and fill in the AB equals shown by the dashed lines. Finish the SM charts connections and then write DA, DB, and Z equations below. Z equals 0 if there's no conditional assignment block with Z equals 1. So we're not going to, yeah. So yeah. All right. Okay. So we start off with, let's do the flip-flop state assignment. So S0, just straight binary, 0, 0, 0, 1, 1, 0, and 1, 1. Okay. You probably can't see this bottom.
No, we can't.
Oh, you can't see it at all. Yeah, that's right. Never mind. Okay. Okay. Yeah. Okay, let's see now.
This is Mealy.
All right. Okay, everybody ready? All right, so everybody can see that okay? All
Yes.
right, good.
Yes, sir.
Yes.
All right. Okay, so we're in S0. Okay, so X comes in, so we have a state box here, S0, and it means that we have nothing. We have a decision box here, X. So if X is 0, we're going to go one way. If X is 1, we're going to go another way. Because remember that that Z equals X, except when we have 4 zeros, and then on that last 0, we change that 0, we make Z equal to 1 instead of 0, which it would normally be. All right, so here we have on a 1, of course, we're going to output Z, which means Z equals 1. We don't write that in, we just write Z if it's going to be 1. And if Z does not appear, then it means it's 0, okay? All right, and then we have, so if we get a 1, where should we go? So what are we trying to keep track of? So here we have nothing, here we have 1, 0, here we have 2, and here we have 3. So we're keeping track of zeros. So
Yeah, so we just gonna go back to S1.
that's correct. S0, you mean?
Oh, S0. Yeah, always.
Okay.
Yeah, the first one. Yeah.
And if we get a 0, now we're going to go over here to S1. And you don't see a Z output because Z will be 0.
Mhm.
Okay, here we've got our first 0. Now we have a decision. If we get a 0, we're going over here again, and Z is still going to be a 0. But if we get a 1, Z will be a 1. But where should we go?
We should go back.
Back to S0.
That's right. Okay, now we're in S2. Same thing. We get a 0 or a 1. Where should we go if we get a 1?
Go back to
S0.
Yeah. And then where should we go on a 0?
you go to S, whatever the next one is.
3. Yeah.
Mhm.
Now we're in S3. Now this is a little screwy, but so the next X comes in. Now, since we're told to reset after the target. So let's say we don't get a target, we get a 1. So Z should be 1, and we go back to S0, right? Where we always go. And where do we go if we get a 0?
We reset.
Yeah, we still reset, and we still output a Z equals 1. So the truth is, we don't even need this. We can just put a Z block here, and this can automatically go back here. There's no reason to we don't even have to consider X because it doesn't matter.
So that's like a way to trick us pretty much to make sure that we know what we're doing.
Well, it doesn't matter how you write it. You'll still get the right answers.
Okay.
All right, so now let's D8. Okay, so we want all the paths into all the blocks where our A equals 1. So where does A equal 1?
On S2
2 and
And-
and
S3.
S3.
Okay, so we have one path into S2. It comes from from S1, which
A
is
prime,
B.
A prime B, yeah.
A prime B, and
X is 0,
so X
but
prime.
X prime.
And then we add to that the one path into here, which comes from here, when X
A
is
B prime when
Yeah.
X is X prime.
A, B prime, X prime, correct. All right, let's do the DB.
So wherever B is 1, that would be S1
1
and
and S3.
So we know
And it-
same thing here. So we just need add the new one, which would be,
which would be, is
A
that one?
prime, A prime, B prime, X prime.
Yeah.
I think.
A prime, B prime, X prime plus A, B prime, X prime. And the nice thing here, these can be combined to B prime, X prime. And then Z, okay, so Z is going to be a little more problematic.
You said we were looking at B wherever B is 1, right?
Yeah,
All right, so B is 1 and S1, so that'll be A B prime. X prime.
yeah, we already added that. We already added that down here. Because
And
we
where
already-
you get the A prime, B prime, X prime? We get that one from.
So that came from here into here.
Oh, right. Okay, cool.
Yeah. So the one path, so this was the one path and this was the other path. Those are the two paths we needed.
So you're not gonna use S3 because B is a 1 there too.
No, I copied it from here. We already did it there.
Are we supposed to have like 3 terms? Okay, that's 1 term.
So this comes from here, A, B prime, X prime.
Yes,
Into, right?
yes. All right, you know what? Never mind.
Okay,
I'll answer my own question. Okay, sorry.
good. That's all right. Okay, and then Z. Okay, we've got a Z here, we've got a Z here, we've got a Z here, and we got a Z here. So the one
But I-
here is just going to be AB. But if you wanted to put ABX and ABX prime, then you could combine them. So ABX plus ABX prime, you could combine those and just to AB. So we know this is just AB. So we have AB for this one, and then we need this one, AB prime X prime. Plus, what about this one?
That's gonna be A prime B X prime.
Yeah. Oh, sorry. I misled you. This one is correct. This one is screwed up. All right, because there's no Z on this. There's the Z's here. So it's A, B prime, X, because that's the Z. The Z, the 0 doesn't go through Z. So it's A, B prime, X. And the same thing here, A prime, B, X, right? Because there's no Z here. That doesn't exist. So it's A prime, B, X, and then finally this one, A prime, B prime, X. So this is the final answer for that. Okay, and we can combine these two, and we can combine these two. So these two will combine to A prime X, and these two will combine to B prime, B prime X. So it's AB plus B prime X plus A prime X.
And we can put this in a K-map to reduce it.
You could, yeah, and you can also, in this case though, you know that there's no don't care terms, because you have all the combinations of A and B are used. Because you have 2 flip-flops and 4 states, so it comes out. All right, let's look at this one. I always put something like this one on the test, so this is a good one to do. Okay, so we'll knock this one out. and then I'll do some questions and then we'll quit, because I still have to get the test ready. I have to make a few more changes and get them plugged in. All
When
right.
are we having the test?
Well, it's going to start at midnight tonight. Oh, that's right. Okay, for the in-person session, everybody wanted to do it, start it tonight and go to Saturday night at midnight or 11:59. So that's what
Yes.
we'll do. For the people that are in the online class, let me finish this and then you guys can tell me when you want me to do the test. Do you want to do the same thing or do you want to do it a different time?
The last day possible.
The last day possible
Yes, sir.
Yeah, I would say either next Wednesday or Thursday.
of next week? Okay. So how many want it Thursday of next week?
Whatever's the last day, I'm with that.
Thursday works for me.
Okay, you guys want the latest day possible.
Yes, sir.
Let me see. I don't know. Let me look at the final exam period and see. Although it makes it a little bit easier for me to do grades if I have an extra day or so. But that's okay. Let's see. Content. Actually, let me do this.
I gotta go. Professor, it was nice.
Yeah.
Are you gonna post?
I'll post
right?
it. Yeah, I'll post it.
Okay. If I have any other questions between now and whenever, I'll email you. Please check your email.
Yeah, but you've only got about an hour, 2 hours, 3 hours.
Yeah. Yeah. Well, I'm not gonna to message you when I'm doing a test, but I'm just saying.
Yeah. Right, because I'm not going to help you then.
Yeah. Well, definitely not. But
And
yeah.
the test
So, yeah,
starts
but
at midnight.
yeah. I gotta go though. So I'm gonna talk to you later. Well,
Okay. All right. Okay. Let's see. Let me put UTSA. UTSA. Oh crap! I didn't want to do that. Okay, let's try it again. UTSA.edu. Okay.
So Professor, just to clarify, when exactly is the online test?
The online test starts at midnight tonight. Oh, so the online test, we haven't said yet. That's what we're going to look at.
Oh, okay.
I think the semester ends on the 10th.
Yeah, let me see. I think I have to submit grades on the 13th. Oh, this is stupid. I don't even know where this is anymore. They've just screwed this up so bad. Do you guys know where to look to see the final exam schedule? I can't find it anymore. I give up. It's really
It's in our email. Let me go look it real quick.
God bless. I hate this. Maybe it's here. Does it say it here? Final exam schedule. Oh, I can find the library hours. That's great. Oh, final exam schedules. Fall. So looks like Friday, December the 10th is the last day of finals. Yeah. All right. Last day is the 10th. So do you guys really want to do it the 10th? So what is the
I'm
10th?
cool with either the 8th or the 9th.
All right, let's just do it on Wednesday. We'll do it on Thursday the 9th.
Okay.
Okay, that works for me.
Okay. All right, that's great. That's good. Okay, Thursday.
You can do it any time that day, or
Yeah, I'll make it available from early in the morning, like starting at midnight, which is really the very first incident day. Wednesday at midnight is the beginning of Thursday. Actually, it's not Wednesday anymore. Right?
How many questions is the exam?
I think it's about 100.
Okay.
Actually, let me see. Maybe it's not quite that many. How come I can't see that? Oh, yeah. No, okay, so I think it's 80 some odd now. And I'll give you 2 hours. And you won't be able to back up, you see one question at a time, randomized, but you'll have 2 hours and, it's open book.
And it'll be due Thursday at midnight, right?
Yeah, you have to finish it no later than Thursday at midnight.
Okay.
Yeah, you can start it, as long as you start it before midnight, you'll have 2 hours.
Is there any way that you could open it like earlier and just leave it open for a couple days? Because
Well, I kind of don't want to have it open for a long time because I think that just invites problems. So you'd
Okay.
like to have it earlier?
I mean, yeah, like I'd prefer to have it on Monday just to get it over with. But if it doesn't work for everyone, it's fine. I was just wondering if you could like keep it open for a couple days
Yeah.
so we could choose.
Put her on mute, please.
Yeah, I'm the same as well. I would also like it earlier.
Put her on mute, huh? Well, okay. So what I can do, I can leave it open for 2 days and we'll start it then. You can take it Tuesday at midnight, okay, all the way to Thursday at 11:59. So Tuesday at midnight would be actually Wednesday, but you could take it that night if you really want to. So will that help you a little
Sweet,
bit?
thank you.
Okay, we'll do that. All right, let me write that down so I don't forget. We'll set that up. Tuesday, so Wednesday, so basically Wednesday, Thursday. But we'll have it open all day, both those days.
And we can start it Thursday, 11:59, right?
You can, no, that's the,
Or it has to be done by 11:59.
you can start it as before 11:59.
Okay.
I guess you could even start at 11:59. You just can't, I wouldn't wait till 11:59 and find out. Do it at
Right.
11:58. If you 11:58, you're okay.
Okay, start at 11:58. Got it.
Yeah, well, I don't recommend that.
Yeah.
You'll be working until 2 a.m.
Yeah, just trying to get some room in there.
Yeah. But you can do that. All right, okay, let me finish this one. So everybody can see this one here. So a sequence detector X and an output Z. So it's a standard, we've just got a standard, standard deal where we have a black box. We have X going in and Z coming out, X going in. And here's our network we're going to design. Okay. So Z outputs, Z should be 0, not F equals 0. Z should be 0 unless it sees the sequence 100 or 000. 3 zeros are 100. And okay. And when you see this, the target, then Z equals 1. The network resets as soon as the target can't be realized, discarding the value just received. If the target is realized, it also resets, so the next value starts the next possible target. Okay. All right. So we start in S0. So because we have 2 targets, 100 and 000, it doesn't matter what we get. We're going to go to S1 regardless, because our first value will either way be a possible target. So we'll do that. And then in S1, and it's also a Moore network. So our outputs are associated now with our nodes. So that's the Z output, that's the Z output. So Z is 0, Z is 0, because we don't have a target. And then in S1, if we get a 1, then we can't get a target. So we'll just discard that value and go back to S0. And we don't have any outputs on these links because it's Moore. But Z is 0 in both nodes. So Z will be 0. But if we get a 0, now we have 2 zeros. And so we have either, we either have 1 0 or 0 0. So we have the first 2 items of our possible target. And we output a 0 for Z. So we'll say Z equals 0 here. All right. And then if we get 1 more 0, that's a target. That's this is S2, this is S3. And so now Z is going to be equal 1. and it's target. Okay, and that's on another 0. Now, if in S2 we get a 1, we're going up here because we can't get a target. Now in S3, it said, if the target is realized, it also resets. So the next value starts the next possible target. Okay, so from S3, whatever we get, we want to go over here to S0 on a 0 or a 1, because that'll be our first item of the next possible target. Okay, so from S0, we go to S1 regardless. From S1 on a 0, we go to 2, and we go back to S1 on a 1. From 2, we go to 3 on a 0, and back to S1. And from 3, we go to S1 regardless. Here we output a 0, here we output a 0, and here we output a 1. Notice there's no X, there's only a single column there because it's a more. And the meaning of the states, so we have nothing. Here we have our first item. Here we have our second. Here we have our, and here we have target. And also reset. Okay. All right. And then let's see. I can't remember. Did I get to? Yeah, I think that's it. On page 46. Well, how did we not? Let's see. Let me print out the last copy. Hang on. Let me. So we have more. Okay, yeah, we do. Oh, okay, here we go. Yeah, I thought so. Did we do this one? Yeah, we did. Maybe not. Yeah, we did that one. We did that one. Oh, we didn't do this one. Okay, yeah, but okay, we're gonna do this one. All right, so yeah. All right, so so here, so let me print this page out. I don't know why. Maybe this will print correctly here. We'll print, and then and I think that is page 6. Yeah, it's page 6. Okay, print. No. All right, I printed out the wrong thing. Print out page 4 again, but now I got it. Okay. I'm just gonna do this. Okay. So here's the problem. Okay, so I'm going to go over how to do these, and if you follow this, it's the same as on the last test, but I usually put one of these on the final too. So I want you to kind of know how to approach these. And I did go over this before, but so this is kind of important. All right. So first you read the problem carefully. Using the JK flip-flop picture, write in the tracing for Q in the timing diagram. Assume that the time for the output to change after the active edge of the clock or the assertion of clear not is 5 nanoseconds. Assume setup and hold times can be ignored. Note that the flip-flop has an asynchronous clear not, and you should know how to tell if it is active high or active low. Initially, Q equals 0. You should mark the active clock edges and the time when the asynchronous input is active with, some kind of slashes or something. So this flip-flop is a rising edge or a falling edge flip-flop. So, okay, so somebody tell me, is it rising edge or falling edge?
Falling.
Okay, it's falling edge. That's correct. All right, so, and then is the asynchronous input active high or active low? The clear not.
Low.
It's active low. Okay, so let's look at this. So I'm gonna switch this. All right. Make sure we got this. Okay. All right. Now, so the first thing that I recommend you do, so here's our asynchronous input. It's a clear knot, shows up right here. And here it is right here. Now, tell me, is it active here or is it active here?
On
A,
the left.
B. Yes, it's active here. So I'm going to mark it here like this. And then that's where it's no longer active. So it's active right off the bat. Now, which edge is my clock? Is this the edge or is this the edge? A or B?
B.
That's right. But I'm not going to mark the edge here because it's blocked by the clear knot. This edge is blocked, this edge is blocked. So these are blocked, blocked, blocked. Now this edge, on the other hand, is not blocked. So we're going to highlight it. And we'll just mark this all the way down here. And then this edge is not blocked. So we'll mark it all the way down. And this edge is not blocked, and we'll mark it all the way down. Now, the other thing I know is that there's a propagation delay of 5 nanoseconds after the active edge of the clock or the assertion of clear knot. So clear knot is asserted here. But we already know that Q is 0. So Q is going to start off 0. So I don't really have to worry about when the clear knot's asserted because it starts at 0. All right. But the active edge of the clock, I know that there's a 5 nanosecond, and each division is 5 nanoseconds. So I notice that so this is where there could be a change. The change won't happen on that active edge. It's going to happen here. Change won't happen here. It's going to happen here. Change won't happen here. It's going to happen here because it's 5 nanoseconds after that edge. But what does happen on the edge is it's going to read the input, and that's going to determine what happens. Now, this is a JK flip-flop. So the way you have to think about JK flip-flops is that J sets and K clears. And you can think about clear with a K in it if you want. All right, so J sets, K clears. If they're both 0, they hold. And if they're both 1, they toggle. All right, so I don't have to worry about what's happening here. I know that Q is going to start off and it's going to be 0 and it can't change until it gets to here. Might change there, I don't know. Okay, at this active edge, what is J?
1.
J is 1. And what is K?
1.
1.
1. All right. At this active edge, what are J and K? What is J?
1, 0.
J
Right.
is 1.
And K is 0. And at this active edge, what do we have?
1, 1, I
1,
think.
1. Yeah, 1 and 1. All right. So what's going to happen at this active edge?
It's going to toggle.
It's going to toggle. So we'll just mark this up here as toggle. What's going to happen at this edge?
It's going to stay. It's going to set.
It's going to set. If it's already set, it'll just stay. And what's going to happen here? At this active edge?
Toggle.
Toggle. All right. So I know here it's going to toggle. So it is 0. It's going to happen 5 nanoseconds after it read the J and K. So it goes up, stays here, can't change till it gets to here. Going to set. That's not going to change because it's already set. And then here it's going to toggle. So it'll go back down. So that's all there is to that problem. All right. Let me just go through a few questions and then I'm going to let you guys, I think I'll do this. I'm gonna stop the share screen here and I will. All right, so, okay, so let's see. All right, so what's the big difference between Mealy and Moore?
The
Really
outputs
depends
are
on the outputs.
dependent on the inputs.
So for a Moore, the outputs are associated with the states, and for a Mealy, they're associated with the states and the next inputs, right? So in the calculation for a Moore, you'll never see an X. You'll never see an input variable. They of course affect the state that you're in, but once you're in that state, the outputs only depend upon the fact you're in that state and not what the next input's going to be. Whereas when you see more outputs, they often do have X's associated with them, or various inputs, maybe X1, X2, X3, whatever. All right. Okay. When we went through state tables, one of the things, once we got our state table, what did we want to do next? What was our typical next thing to do?
Is a transition table?
Well, okay, so you skipped over a couple steps.
Okay.
So you skipped over flip-flop state assignment, which is how you get to the transition table. But you also skipped over another step. So let's say your state table has a lot of steps in it, and you're hoping, what are you hoping? You're hoping you can do something about that, right? Maybe reduce it.
Yes, sir.
So if you have a problem where you read in a number of states and then reset and the number's fixed, you always read in X number of states and reset, whatever X is, or well, N number of states and reset, where N is a constant. In that scenario, then we can look for redundant states. And if we don't have a problem like that, or even if we do have a problem like that, we can also look for equivalent states using that implication chart, which looks like a checkerboard cut on the diagonal, or we can also use distinguishing sequences that we talked about in the in-person course. All right. Are we good? So how important are state machines?
On a scale from 1 to 10?
Well, or whatever, yeah.
10?
Well, yeah. In other words, they're in the real world. We use state machines for almost everything we do. It's just and in some cases where we don't use state machines, we probably should. You should probably use state machines when you write code, but we don't always do that. But especially with an embedded design, you should probably write a state machine. I don't push that in Micro 1 nearly as much as I should. I'm working on that, but
It speeds up our technology, right?
not so much that. That's more to do with hardware description languages, but state machines are just a good way of approaching problems. That's very, it's pretty robust, and it's easier to debug. It's easier to figure out your logic errors and fix them. So it's really good to do state machines. But what happens most of the time is people just start writing code. They kind of go off half-cocked, and as a result, they go round and round and round trying to debug it and get it to work, and they really have a hard time finding where their logical errors are. Well, a state machine really helps you with that. All right. So when we store information on a computer, what do we use to store information in computers?
Zeros and ones.
That's true. Yeah. And how do we know whether it's a picture, a floating point number, an integer, a listing from the telephone book? How do we know what it is?
Ones and zeros?
Well, they're only going to be ones and zeros. How do you know what they represent? Well, we have to use codes, right? We use binary codes. We use ASCII codes. We have codes for video. We have codes for pictures. We have codes for audio.
That's kind of what I meant, but yeah, you said it way better than I did.
Okay. What'd you expect, Jose?
Oh,
I mean,
All
he
right.
wasn't wrong.
No, it is ones and zeros. That's true, except in a flash drive. And then in the flash drive, we don't have ones and zeros anymore. We store them as 1, 2, 3, or 4, or 0,
Right.
1, 2, 3.
I'd actually had a quick question about that state assignment. So you mentioned that's just like say for 4 variables, we'd just be using that. I produce some chart where we go down
Yeah.
like 1, 2, 3, 4, and then flip the bottom row on the next one, and this and that, right?
Well. So
And
when you
just to see which one would give the shortest input assignment to a D flip flop, and that's the one we go with, right?
yeah. So when we do our flip flop state assignment, we talk about adjacent assignments, and we have a couple of rules. States of the next states of the same state should be adjacent, and states that have the same next states should be adjacent. And then we also have a rule for the outputs to help with the output matrix, and that is states that have the same output should be adjacent. Okay, so we try and apply those kind of in that order, and sometimes we only can, the rule only applies 50%. So so we still try and apply it, and usually we use a K-map to assign them. So if we've got 3 flip flops, we'll use a 3 variable K-map, and the way we set that up, if you put your states in adjacent boxes vertically or horizontally, then they'll only differ by 1 variable, and that's what we mean by adjacent. But you don't have to use a K-map for that, but you just want them to. But it's just a good graphical way of doing it and keeping them and where they're only going to differ by 1 variable. Yeah. Okay.
Professor.
Yeah.
So when we were doing the 7 segment displays,
Mm-hmm.
and then we started using the registers further on after that.
The registers.
Yeah, like shift registers and stuff like that. Like, is that sequential design?
Yeah. So a shift register has a clock because all the bits have to change at the same time.
Right.
So it's sequential. Yeah.
And so a melee and the more circuit, they're also sequential designs.
Yeah. Yes.
They're just different kinds, right? Different types.
So melee and more are different in the way that the outputs are determined. In a more, the outputs are just locked into the node, and in the melee, the outputs are associated with a node and the next inputs that come in.
So our shift registers, melee circuits, and more circuits, are those all state machines?
Well, so shift register is a device, and it's not really melee or more per se. I don't know.
Sure.
I guess you could describe it with a state machine. Yeah. When what you'd say is that when you went from state 1 to state 2, all the bits would shift one way or the other. But we don't usually use a state machine because it's maybe not all that. That may be one case where state machine's not super helpful. So not all algorithms, not all sequential designs are state machines. A lot of times we will do sequential designs and not use a state machine, but it's a much more, a state machine would be a good idea most times because it's a lot more I don't know what the right term would be. It's a lot more organized way to implement a sequential design.
So for the purpose of this test, our state machines are going to be pretty much focusing on the melee and more circuits.
Yeah, right.
Okay.
Yeah.
Okay.
Okay. And so how come, why did we talk about, SOP, POS, and then pretty much NOR, and NAN? Why didn't we look at, it turns out that's only 4 of the possible 8 combinations that are complete logic sets with our 4 standard gates of AND, OR, NAND, and NOR. Why did we just look at those 4?
They're the most common.
Yeah, that's really their most common. We use a SOP and POS for the design side, and then a lot of our devices are NAN or NOR construction. Okay, I think I'm going to stop there. Let me give you a chance to ask questions, and then we'll wrap it up.
For the purpose of the test, will we have to do state assignments, like pick the best one?
No, I probably won't test that. It turns out it's kind of awkward to test that because if everybody
There's
doesn't
so many
use the same-
possibilities.
yeah, and if everybody doesn't use the same assignment, then how do you grade it, right?
Okay.
So, and it turns out, it's if you're using 4 states, then it is true. You could have you do that. I've tried that on tests because it's 3 or 4 states. You do 1, 2, 3, 4, or 1. You do 1, 2, 3, 4, or you do 1, 2, 4, 3, or 1, 4, 2, 3. Those are the only non-equivalent assignments. But once you get past 4 states, then it's crazy, and you can't really, it's so complicated you can't really make it work very well. So you just have to use the rules, and the rules, there's a lot of ways to apply the rules. So it's hard to test that. I guess I could.
Okay, thank you.
Yeah.
Professor, on the practice exam that you just did you go over number 11 by chance?
No, I'm not going to have one on the test like that. It's confusing. I'm not going to do that.
Okay, awesome. I'm good then.
Yeah, it's an example of a problem with 2 inputs, and I didn't really give you the problem. I just gave you the state graph and then asked you to fill in the state table, which is actually super easy. But doing a problem with 2 inputs from the beginning can be kind of confusing. Yeah, so I probably won't do that.
On some of the practice tests, the question is, a sequence detector has 1 input X and 1 input Z. Will all the inputs guaranteed to be properly set up for each clock pulse? It's one of those type of questions, and it has S0 over 0, and then it goes to S1 over 0, and it says,
what are you describing, Jose? I'm not tracking at all.
It's a sequence detector problem, and it's one of those problems where you go from S0.
So what is the sequence we're detecting?
Well, it says it has 1 input X and 1 input Z, and it wants the network outputs a F equals 0 unless it sees the sequence 1 1 1 or 0 1 1.
Okay, yeah, we just worked a problem like that.
Yeah, and on a different example, sometimes I get confused because it says S0 goes to S1 and it says X equals 0 or 1. And that's because the first number, since it's searching for 1 1 1 or 0 1 1, it's the first detected target, regardless if it's 0 or 1 because of the sequence, right?
Right.
Okay. For some reason, when I explained that to you, I kind of got it.
Yeah, it was confusing. Yeah, what you can think of that, you can actually think of that as the first input as a don't care, really. Doesn't matter what it is, it'll count as the possible start of the target.
Okay.
Oh yeah, so as the start of the target, each new input is going to be input on the low order bit, right? I think it's how we did it, like to the right of, like, say it's looking for 100, so we're looking for a 0 input that would start.
Yeah. I usually think of it. I usually, when I'm looking when I'm writing inputs, I usually write them with the first, the first input that came in on the left, the next to the right of that, the next input that came in to the right of that. Yeah.
Okay, thanks.
Yeah. And I usually do say something about that if it's confusing. I'll try and give an example. Okay, well, it's been a couple hours. Why don't we wrap it up unless anybody has any other burning questions?
Yeah, I have a question. As far as grades go, you said the 13th is when you're gonna post them all?
Yeah, that's when I think they're due the 13th.
Okay, yeah, because I still don't have a grade for my group project.
Okay. So I think I just looked at that. Hang on. So what group were you in?
I was with Ben, Nani, and I think Nick.
All right. So let me see. Let's see. So is this? Let me see which one this is. Okay, let me change. You're in the online class, is that right?
Yes, sir.
Okay, let me pull it up. Look at it real quick. Let's see. Great. There we go. Let's see. Oh, I think it must be here. Oh, here it is, I think. No, let's see. Let's see. I have to find it. Yeah, here we go. Right. Okay. So Abel. Yeah, you have a grade, Abel. Why do you think you don't have a grade?
I was checking my grades and it says that it's
so
upcoming.
where are you looking for the grade? So look
on
in the column.
hand.
Look in the column, upload group project video to this link. That's the column that your grade's in. Yeah, anyway, you have a grade.
Yeah, okay. I was just curious. I guess I'm looking in the wrong spot.
Yeah, right.
Hey, Professor, so there's no class tomorrow? Like
the semester's over.
Yeah, okay, awesome. Well, I appreciate it, and thanks for all your help. And do you approve people getting into micro?
Yeah, it's as long as you. The only requirement is you have to. I think you have to pass logic designs off.
Because I think I registered for it, but it says it's. I had to do a prerequisite override, and I'm still waiting on a response. And I didn't know if you approved those or.
Yeah, no, I probably would do the prerequisite override. I haven't really. I've been super busy the last couple of days with Micro 1 and DSD because we had the big demo days. But I'll go through and take care of those. Yeah, there's been a few days of email slippage, but yeah, if you have some, if you have a prereq override, yeah, I'll fill that out and take care of it. No problem.
Thank you, Professor. Appreciate your time. Thanks for a good semester, and hopefully see you next semester.
Yeah, no problem. We will, as long as we're still both here.
For sure.
All right. Okay. Last call. All right. I will. So I'll post this. I'll post this to both the online and the in-person course blackboards.